So, welcome to module 19. This module is about joint distribution of random variables. So, suppose I am given a probability space omega p. Now, what may happen in many situations is we may be interested in two or more numerical characteristics of the sample space simultaneously. To illustrate this, consider the following example. Suppose consider a random experiment which is casting a red and a white die. Now, in this case my sample space is collection of all those ij's such that I and j could be any numbers from 1 to 6, where when I say ij is in omega, I indicates the number of spots on upper faces of red die and j denotes the number of spots on upper face of white die. What I do is I define two random variables over here, x1 from omega to r and x2 from omega to r. They are defined as follows. x1 ij is defined as I plus aj. So, x1 does is it maps outcome ij to I plus j, which is nothing but sum of numbers on upper faces of two dice. What x2 ij does is it maps the outcome ij to mod of I minus j. So, that means x2 for an outcome ij gives me the absolute difference of numbers on upper faces of two dice. Now, it may happen that I may be interested in these two quantities simultaneously. Now, that amounts to considering a random vector x from omega to r2, where x is x1 x2, x of ij is defined as, because x is defined for each element of omega. So, x is defined for each ij, that is defined as x1 ij comma x2 ij. So, that is defined as ordered pair x1 ij x2 ij, where ij belongs to omega. So, I may be interested in this function. Now, such functions are called random vectors. So, a function x which is x1 x2 xp from omega to rp is called a p dimensional random vector. Now, here rp is the p dimensional Euclidean space, which is collection of all those x1 x2 xp such that xi lies between minus infinity to infinity. So, this is basically r cross r cross r p times. Now, as I did in the univariate case, that is p is equal to 1, for a set A in rp, define its inverse image as collection of all those points in the sample space which are mapped inside the set A. So, that is collection of all those omega belonging to omega such that x omega is in A. Now, with this I can define a new set function px from p of rp to 0 1, and how I define pxa? Pxa is defined as p of x inverse of A, which is p of all those omega belonging to omega such that x omega belongs to A belongs to p of rp. So, what has happened is you had a sample space omega, you had a function x from omega to r, you had a probability space omega p. Now, from here through a random variable x, I have defined, now I have come to real line. Then I have a set function pxa which is defined for any subset of real lines. So, it is defined p of r and px. As in the univariate case, it can be shown that this function px is a probability function, and that is what we do next. rp, prp, px is a probability space, that is px is a probability function on p of rp. The proof is exactly same as the one for p is equal to 1. So, I will not give the proof here, you can simply construct a proof on the same lines as for p is equal to 1. Now, this probability space, as in the univariate case, is called the probability space induced by random variable x. So, the probability space rp, prp, px is called the probability space induced by random variable x, or simply the induced probability space. So, this is the diagram. So, to begin with, you had space omega p random variable x takes you to a different space which is Rp, P of Rp and Px. So, things done for univariate case have been extended in an obvious manner to the p dimensional case. Now, let me introduce some notations. For any subset of Rp, x belonging to A means collection of all those omega such that x omega is in A. So, that means all those outcomes which are mapped to A. Now, for A is equal to A1 A2 AP and B is equal to B1 B2 BP, A comma B nothing but A1 B1 cross A2 B2 cross AP BP, which is collection of all those x, x1 x2 xp, such that x size lies between AI to Pi. So, it is kind of a p dimensional semi closed rectangle. And what would be its vertices? Its vertices would be Z1 Z2 Zp, where Zi is anything between Ai to Pi. So, in all it will have 2 to the power p vertices. For example, let us look at what happens in the case of 2. So, x1 was between A1 to B1. So, A1 B1 A2 B2 and their cross product is this. So, this is this, and what are its vertices? Its vertices are Z1 Z2. The first one ordered pair has to be A1 or B1. So, that means Zi second has to be A2 or B2. So, in general when you are dealing with p dimensions, the ith coordinate in Z1 Z2 Zp has to be either Ai or Pi, as it is happening over here. For example, if you look at this is a 2 dimensional rectangle. What are the vertices over here? A1 A2, A1 B2, B1 A2, B1 A2. So, in general a vertex is of the type Z1 Z2, where Z1 is either A1 or B1 and Z2 is A2 or B2. So, when I am dealing with p dimension, my typical vertex would be Z1 Z2 Zp, such that Zi is either Ai or Pi. So, this AB is a p dimensional rectangle A1 B1 cross A2 B2 cross AP BP, whose vertices are Z1 Z2 Zp, where each Zi can be Ai or Pi. So, that means in all there will be 2 to the power p vertices. In the case of p is equal to 2, there were 4 vertices. So, that is what is described over here. So, let us call delta p, and this is basically delta p AB. This is collection of all those Z is equal to Z1 Z2 Zp belonging to Rp, such that Zi belongs to Ai Pi, I is equal to 1 to p. So, this is a set of all vertices of p dimensional rectangle AB. Now, when you are talking about vertices, in case of p is equal to 2, the vertices are A1 A2, A1 B2, B1 A2, B1 B2. So, although I know that the ith ordered pair is Ai or Bi, but how many of them are Ais, that is determined through delta Kp. So, this is set of all vertices of p dimensional rectangle AB is same as summation k is equal to 0 to p delta Kp AB, where in delta Kp AB is that vertex where k of Zi's are Aj's and p minus k of Zi's are Bj's. So, to see this, let us consider the example of p is equal to 2. Delta 2 is the set of vertices where delta 2 is the set of all vertices. So, B1 B2 A1 B2 B1 A2 A1 A2. So, you see first ordered pair is A1 or B1 and second ordered pair is A2 or B2. Delta 02 is of those vertices where 0 AIs are occurring. So, that means both the factors are BI. So, B1 B2. Delta 12 is the set of vertices where exactly 1 AI is occurring. 1 AI can occur either A1 or A2. So, that is A1 B2 and B1 A2. Delta 22 is the set of vertices where both are AIs. So, that is only one vertex A1 A2. So, let us introduce few more notations. For A is equal to A1 A2 AP and B is equal to B1 B2 BP, minus infinity to A written in this form is collection of all those Z belonging to Rp such that Zi is less than or equal to Ai. So, here A is closed. A open, infinity open, this is collection of all those Z belonging to Rp such that Zi is greater than Ai, because A was open over here, I is equal to 1 to p. Then open A and B, is collection of all those Z belonging to RP. It is open on both the sides. So, Z I is between A I to B I, I is equal to 1 to P. So, other way to write down this would be, for example, A 1 B 1 cross A P B P. Other way to write this would be nothing but A 1 infinity cross A 2 infinity cross A P infinity, and so on. Similarly, you can define closed A B, semi closed A B, minus infinity to A open, A to infinity closed at A. One can define similarly. Now, when I have two vectors A and B, A less than or equal to B, that means there is an inequality component wise. So, A less than or equal to B would mean A I is less than or equal to B I for I is equal to 1 to P. Similarly, A less than B means A I less than or equal to B I for all I is equal to 1 to P, but there is a strict inequality for some J, or in other words, A is less than B if A is less than or equal to B, but A is not equal to B. So, under these notations, let me give this definition. So, suppose X is a p dimensional random variable. The joint distribution function of X is the function f x from R p to R defined by this. F x x is same as p x minus infinity to x, which is same as p of x inverse of minus infinity to x, which is same as probability of all those omega belonging to omega, such that x omega is less than or equal to x, which is equivalent to saying that x I omega is less than or equal to x I for I is equal to 1 to p. So, that is what this means. So, this is called a joint distribution function of x 1, x 2, x p. The joint distribution function of any subset of random variables x 1, x 2, x p is called a marginal distribution function of f x x. So, when I am talking about the joint distribution of a subset of random variables, essentially we are talking about the marginal distributions of subset of x 1, x 2, x p. So, let us take this example. Suppose x 1, x 2, x 3, x 4 was a 4 dimensional random vector and f x was a distribution function. Then f x 1 is a distribution function of x 1, f x 2, x 4 is a joint distribution function of x 2, x 4, f x 1, x 3, x 4 is a joint distribution function of x 1, x 3, x 4. These all are marginal distribution functions of x, which is x 1, x 2, x 3, x 4, or these are also called marginal distribution functions of f x 1, x 2, x 3, x 4. So, when we talk about the distribution function of a subset of random vectors, we are talking about marginal distributions.